Hello everyone, how is it going? Well, let's directly go on to our lecture today, and we have already seen about functions, and today we are going to define more informations on functions as well as on inverse function. As I told you in the last lecture, I will give you more examples on inverse function. Let's see what it is. So before which I want to just redefine these terms. So just imagine a function is like a dye you use to color eggs. So a white egg is the input, as if like you have the eggs to be, say you have in this example what we have is like you have an egg that has been given as an input, and the function blue, it actually dyes and gives you result as blue egg. So what we have here is the white has been turned to blue. S. That's the basic idea. Once you go through the function, the whole value changes. White egg is the input function. The white egg is the input, and in the function blue dye, we get the result as blue egg. In other words, the inverse function, it undoes what the function does. In other words, we just saw that the white has been turned to blue. Now if you turn the blue to white, then that is an inverse function. Yes, that's what we are going to consider about the inverse function. Let's see here with some numbers, in fact. So you have 3, and it goes into the function x square, it becomes 9. Yes, now if you want to do an inverse of this, it goes through the inverse function, which is root of x, and it produces the value 3, the original value. As once things goes into the inverse function, it has to produce the same result as the original. Let's consider another example where we have 5. It goes through the function x square, it produces the value 25, and this 25 goes through this inverse function f inverse of x, that is root of x, and that produces you the result 5. That's true for any values that we have. It's 11. We have the function and the inverse function. And if you want to represent things graphically, let's see, graphically x and y values of the points are switched here, and say we have this point 4 comma 7, and 7 comma 4 is the inverse of 4 comma 7. Minus 5 comma 3, the inverse would be 3 comma minus 5, just the reflection of these points. Yeah, that's a simple example for us to understand. Let's say we have a series of values. If a function y equals g of x contains the point x is 0 to 4 and y is 1 to 4, 8, 16, then you have the inverse function y equals g inverse of x, which is, in which case x is 1 to 4, 8, 16, and y is 0 to 4. So this is where the reflection comes in. So where there is a line of reflection, we can see here. So there it is, the line of reflection that clearly marks as the function and its inverse. Let's dive in to more on this inverse function. Okay, remember we talked about the function. We had this domain, 2 domains, domain and codomain. So let's talk about this as 2 set x and set y. Set x as 1, 2, 3, 4, 5 elements, and set y has 2, 4, 6, 8, 10 as its elements. Now we are mapping this set x to set y, and we know an inverse function would reverse the process and maps set y back to set x. There it is. Let's inversely mapping the reverse way. That's the inverse function. So if you map, what we get out of the function is just the back what we had originally. So sometimes we don't have to really go back, like for example 2 goes back to 2 and 1 from where it has come, from 4 to 1 and so on, like just going back. So since going back 6 goes back to both 3 and 5, the mapping going back is not a function. This function is called a many to one function. So we talked about onto function as well, we talked about one to function, and this is called many to one function as well. So only function that pair the y value, the value in the range, with only one x will be function going back the other way. So these functions are called one to one function. So we know that the difference between one to one function and onto function. So when it goes back, if it just goes back to only one value, we can call it as one to one function. How about this one? So this would not be one to one function because everything is being mapped to one element in X. They are not individually mapped to each and other elements in the codomain. So here y would only be used once with X, just like this previous example. Here we have the case in which this function is one to one function because all elements in the domain is mapped to its unique element in the codomain. Yes, each x is paired with only one y and each y is paired with only one x. That's an one to one example of a function. Only one to one function will have inverse function, meaning the mapping back to original value is also a function. So that's the idea why I'm illustrating this point, because either many to one function or onto function does not produces an inverse function. In other words, it does not produces the original value, because when it goes back it hits the something else. Let's determine and see how things would look like from graphical point of view. Let's say it's called a vertical line test. If a vertical line intersects the graph of an equation more than one time, the equation graphed is not a function. That's one of the observations that you have here. So here is a graph. So here in this graph we can see this is the vertical line, and according to the definition in the vertical line test, if a vertical line intersects the graph of an equation more than one time, the equation is not a function. But here in this first example, it doesn't intersect more than one. It's all uniquely placing all these vertical lines. So we could call that this is a function. Let's see another example. So here is this point. The red point is where we are having two intersections coming in. So if it does intersect like this, it is not a function. Here is another one. Okay, so we could say that this is a function because it's clearly not intersecting with another one. Say for example, if suppose let's say I have a point like this, in that case this won't be a function. Just for your example, I am bringing out this. Let's erase it off. Okay. So to be one-to-one function, each y value could only be paired with one x. Let's look a couple of graphs here. Here is the graph. So this is an example of, let's say, look at y values here. For example, y is 3, and see if there is only one x value on the graph for it. So if you have this scenario, this is kind of many to one function, and for any value y on horizontal line will only intersect the graph once, so you will have 1x. Okay. So coming back to the point that I made earlier, actually initially we have seen here is a vertical test, and I have gave an example of a horizontal test for you when I draw this line. So this is supposed to be only vertical test can prove that whether this is a function or not. But whereas we are using the horizontal line here for us to prove that it is many to one function or it is one to one function. Well, when there is an intersection, we can see that that is many to one function. When there is not any intersection, in this case you have the intersection, so we call it as many to one function. But here they are unique, so we call it as one to one function. So if the horizontal line intersect the graph of an equation more than one time, the equation graph is not one to one function and will not have an inverse function. We know that an inverse function is only applicable for one to one function. But if a horizontal line intersect, we would say that that is kind of a many to one function. So in this example, they are unique and they are one to one function. In this example, they are not unique, so they are not one to one function. So in this example, this is what I want to tell you. So this is not an one to one function, but this is a function, but it is not an one to one function. Remember, this is an horizontal line test, it's not a vertical line test. So don't get confused. So let's consider this function f of x equals x cube, and compute some values and try to graph them. Let's say here x values are given and f of x is given to us. So minus 2 is minus 8, minus 1 is minus 1, 0 is 0, 1 is 1, 2 is 2. Okay, let's try to plot a graph. Okay, here it is. So this is how it comes out to be. So is this a one to one function? Yes, you can see that you will have an inverse function if you take the inverse of it. Let's try to undo the cube function. Take the inverse. Let's try to find what the values first. Okay, a cube root of it. F inverse is cube root of x. So that is the inverse function that we talk about, f inverse. And let's take values and see what happens when you tabulate. So x is minus 8, so f inverse is minus 2, minus 1 is minus 1, 0 is 0, 1 is 1, 8 is 2. So let's try to plot it now. Here it is. So this is how the inverse graph looks like. So we can notice that x and y values trades places there. So for f of x is x cube, f inverse of x is cube root of x. Yes, these functions are reflection of each other. Since they provide the exact reflection, we can call it as the inverse function. So geometrically, if a function and its inverse are graphed, they are reflection about the line y equals x, and x and y values trade places. So domain of function is the range of inverse, and the range of function is the domain of inverse. That's why we call it's changing its places. Also, if we start with an x and put it in the function and put the result in the inverse function, we are back in the place where we started. So given a two function, we can then tell if they are inverse of each other. We just plug in to the other and undoes the function or undo. So if f and g are inverse, their composition would simply give back, yeah, that's the inverse function. So here is the composition that we talk about. F composition of g equals f of g of x, that equals x. G composition of f equals g of f of x, that equals x. So if suppose f and g are inverse function, their composition would yield the same thing back, give us the x back, only in this condition. So let's verify the function f and g are inverse of each other. Here we are given with f of x equals x plus x minus 2 the whole square, where x is greater than 2, and g of x is root of x plus 2. Let's try to graph it off. If we graph x minus 2 the whole square, we get a parabolic shift, right? And is it an one-to-one function? So this would be one-to-one, but they restricted the domain and are taking the function where x is greater than or equal to 2. So let's say we are restricting that x is greater than or equal to 2. That's where the limits are given to us, so it cannot go beyond that. So that is it. That's what we talked about. So here f composite of g, we have root x plus 2 minus 2 the whole square. So we are putting this inside, g of x is coming inside, so root of x square is x, g of f of g composite of f is root of x minus 2 the whole square plus 2, that is x minus 2 plus 2 equals x. So we just proved it, they are simply equal. So both of these x, you start with x and apply the function, then finally you come up with the same value x. Yes, they are kind of inverse. So steps to find the inverse function of one-to-one function. So we have definite steps to follow. If you follow these steps, you will definitely come up with this solution. First, f of x, replace f of x with y. Trade x and y places. So you are asked to trade the x and y places. Then solve for y. Y equals f inverse of x. So can we try to do it again? Like initially replace f of x with y, trade x and y places, change it, solve for y. Let's do an example. So f of x is given. So what is the first step? First step is to replace f of x with y. Let's replace f of x with y. So y equals 4 by 2 minus x. The second step, trade x and y places. So x equals 4 by 2 minus y. Third step, solve for y. We are asked to solve for y equals, that's y. So we have to solve for y. So let's try to simplify it. So as you simplify, you get y equals 4 minus 2x by minus x. So y equals the f inverse of x. That's what the solution is. Therefore, f inverse of x is minus 4 minus 2x by x. That's the solution that you have. That's quite simple here. Let's take another example and see how it looks like. And also let's check f composite of f inverse, what it gives here. F composite of f inverse, if you try to do this, you will have 4 by 2 minus 2x minus 4 by x. So that will yield you x. Yes, so that's, we got it. So we ensure that f of x is one-to-one function first. So the domain has to be restricted. So always only one-to-one function can be a inverse function. So here let's see about this graph, the graph of function and its inverse or mirror of one another. We have seen that y equals f of x, and if you want to see its inverse, y equals f of f inverse of x. So that's how it looks like, just the mirror image, and that is exactly the reflection there. There y equals x, right? So we are asked to find the inverse of a function y equals 6 minus 12, that is given to us. Let's follow the step. What is the first step? Switch x and y. So x equals 6y minus 12. Solve for y. Okay, we have solved for y. Y equals 1 by 6 x plus 2. Again, given a function y equals 3x square plus 2, find the inverse. So here in fact we already got or given with y in even both cases. Even here we are not given with the actual function f of x, or we are not given with the function itself, but rather we are given with y and you are asked to solve for y. Eventually you solved it, but in this example we are given with, in both examples, in the last two examples we just saw y is given to you, but in the previous example the function f of x is given. So since y is given to us, let's do like switch x and y. So x equals 3 y square plus 2. So you are asked to solve for y. So that is x equals y square plus 2, x minus 2 equals 3y square, x minus 2 by 3 equals y square, and y equals root of x minus 2 by 3. Yes, we got the answer in the same way that we got for previous example, the same. So we are, in fact we are finding the solution in terms of inverse property. Yes, so far we have seen some example in which how to solve or how to identify an onto function, how to identify a many to one function, and in what cases we can say that an onto function or a one-to-one function is an inverse function. Yes, we have to prove that only an one-to-one function can be an inverse function, and if you have an inverse function, then you know the steps to be taken to solve for the inverse value, and you also know the actual composite property of the inverse function, and in fact you have seen how things will look graphically for the inverse function. Yes, so we already talked about functions, and today we talked about inverse function, and in the days to come we are looking forward to discuss more points on relations and other informations from this topic of discrete mathematics. So until I see you in the next lecture, have a good time and goodbye.